Welcome back. Let's talk about electromagnetic radiation as a way of transporting heat. And the way we have to talk about this is by talking about this idea of black body radiation. And we'll explain what that means in a moment. First off, with electromagnetic radiation, you can be in thermal contact with things without being in direct physical contact. Just like with convection, you could also be in thermal contact without your source and your sink being attached to each other directly. They've got some fluid in between. With electromagnetic radiation, you don't need a fluid either. You can have empty space. Actual space is a very thin plasma, but not a total vacuum, but still. That's not what's transporting the energy. It's the light waves, the photons from the light that are doing it. So when we want to talk about black body radiation, what does that mean? We first need to think about what we mean by the color black and the color white. So by white, what we mean is if it's a perfect white object, it means it's going to reflect it will reflect all the light encountering it. You and I are not, we're not just pure white and reflecting everything. Some of the light that lands on us is absorbed. No matter how pale your skin may be, some of that light is bouncing off, and that's why we can see you. And you don't look like, empty space. The colors that we see in your garments, in my games or whatever, those are not coming from the objects themselves. They're the colors that are bouncing off, that are reflecting off of those objects. The colors that we see for most things are reflected light, and only some of it is being absorbed. We talk about black as being the absence of color, and an ideal black body absorbs all electromagnetic radiation that hits it. So no reflection. And so, well, then what does that work then? What happens then? Well, they release their own light. We also release our own light. And some things are black across one part of the spectrum and not across others. And some are across more of the spectrum and some not so much. So how's this work? So an ideal black body is a perfect absorber of light, but it also means that all the light that you get to see from it is all light that's coming right from it and not reflected. So it also means that it's a perfect emitter of light. Because all the stuff you see coming off of it is its own light, not reflected light. Okay, so what does that look like? Well, folks started observing and describing black body radiation in the 1800s. And so the history lesson here goes something like this. You know, in the 1840s, there's a guy named Gustav Kirchhoff. Observed black body radiation. And so we could see that, okay, an object is going to emit a color spectrum, a broad continuous spectrum of light, red through violet in the visible part of the spectrum, which is all he knew about at the time. He may have known about infrared and ultraviolet in his era, I think. But broad spectrum of light, no lines being blocked, no lines extra that are being reflected. So we get a continuous spectrum. No lines. But what else did this look like? Well, other folks with names like Wien and Stefan and Boltzmann were able to describe the way this looked further. And I'm going to draw a diagram to go along with this. So, if we make a graph, and we say, call this intensity, think of this as brightness, or power per square meter. And we plot on the x-axis here, won't be the x-axis, we'll call this frequency. And we humans perceive frequency of light as its color. Different frequencies of light have corresponding different colors. And the way this works out is like so. So this is brighter, dimmer, and this is spread out across the spectrum. So we've got radio, infrared, microwave, then we've got Roy G. Bouv, or visible light, UV, X-rays, gamma rays. So, the way this works out, it's going to get brighter and brighter the hotter it is. And it's also, like we saw when we were heating up our ball and ring experiment for thermal expansion, and our bimetallic strip for thermal expansion. As we heat a thing up, it starts to glow more towards the red and ultraviolet part of the spectrum. So you get a situation that goes something like this. If something is really cold, oh, this is not a good pen at all. about you? All right. Something really cold, it's fairly dim, and it's bright in the radio part of the spectrum. I'm going to say it's 3 Kelvin, this one. And that's because that's what the background temperature of the universe looks like. That is, all the energy left over from the Big Bang, as soon as the light from that was able to not get stuck in the particles that were around at the time, and able to pass through and get to where folks like us can see it, that all looks like it was spread out and bouncing around with each other and all touching each other, so it all is like the same temperature, this background radiation, when things were really small, close together. And it all looks like it's the same temperature now, which is 2.73 Kelvin and some change. So 2.7 degrees Celsius above absolute zero. Very bright in the radio part of the spectrum. And now you and I, we are a lot brighter than the background radiation of the universe, and we are bright in the infrared part of the spectrum. So that would be like 310 Kelvin for humans. And then you get something like the sun. And the sun is much brighter than we are, and it's glowing in the visible part of the spectrum. And it's glowing pretty flat across the visible part of the spectrum, so it looks white to us when it gets built all together. And that's about 5,800 Kelvin. And then you get to hotter, bigger stars, blue giant stars, and they're like 10,000 Kelvin and or more, and they're brightest in the ultraviolet part of the spectrum. We can't see ultraviolet, but they're a lot brighter in the blue-violet part than they are in the red, so they look blue to us. So this is how electromagnetic radiation plays out with temperature. Everything overall always is going to emit light based on its temperature. Whether or not it's an ideal black body and you've got some other light coming because it's reflecting off of it, you're going to get that light being emitted. So everything is always going to transport energy through electromagnetic radiation, even if it's invisible to the eye, even if it's only infrared. So so heat transport can happen from multiple ways at once. You go and you shake your friend's hand, and you're touching them directly. You've got contact. You have conduction going on there. The heat within your body can be transported to some extent because the blood's flowing around with forced convection. Radiation, you are radiating away infrared light to each other, and the heat is being exchanged in that way as well. Let's see. Let me see if there's any other things. Okay. So that's almost it for electromagnetic radiation for the moment. I want to say one more thing about the Big Bang stuff. We call this radiation the cosmic microwave background radiation. And it's we first observed this in 1965. Some folks at Bell Labs in New Jersey, Penzias and Wilson, the last names, saw this when they were building a big radio antenna. They first thought it was noise, and then they found it was from everywhere in space. It wasn't noise. They fixed it up and found this out. And because it filled all space, and it looked like a black body spectrum, the type of spectrum you get because of a thing's temperature, that tells us that the temperature of the whole universe is really close to the same temperature everywhere. So it's in thermal equilibrium with itself. 13.7 billion light years that way, 13.7 billion light years that way, or they were that far apart 13.7 billion light years, 13.7 billion years ago, and now they're further out still. How did they interact thermally? They had to be in thermal contact with each other. But if they're that far apart now, there's not enough time for the light to get from the one side of the universe to the other. So they had to be a lot closer to begin with. The universe gets to expand faster than light at the far edges. It is expanding. It's how fast it expands does not have the speed limit for inside of it, of the speed of light. And so when you do run the clock backward, stuff gets all on top of each other, and there is enough time in the instances when it was really close for the energy to be exchanged and for things to come to thermal equilibrium. And we see that thermal equilibrium, and this is one of the lines of evidence we have that tell us that we're right about Big Bang theory. At least, to a certain scale of everything being really, 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 really super close together 13.73 billion years ago. We're going to do one more lecture in the series about heat transport on the greenhouse effect, but I'm going to make that a separate video. So we'll come back in a moment with that.